As you may remember, in the previous video, we controlled an RGB LED array color using STM32 microcontroller by using the changed ADC readings resulting from rotating 3 potentiometers knobs, which was inconvenient. So wouldn't it be awesome to do this job using a smartphone? In this video, we are going to use ESP32 with ESP-IDF Homekit to connect it to a Wi-Fi access point to make it act as a smart home accessory, so it can be controlled either from iPhone Home app or by voice commands using Siri, which will do the job for you. Turn off RGB LED.
Okay.
The required steps to set up light bulb example, PWM configuration using ESP-IDF and HSB to RGB conversion algorithm and more will be explained in this video. So without any further ado, let's jump on in. Before beginning, there is a quick note I want to say. You guys may have noticed that recently my tutorials are now focused more on embedded systems and C programming. So if you are interested and you want to see more of such tutorials, make sure you subscribe to Useful Electronics and turn on the notification bell so you can stay tuned. Let's start off with the needed setup for this tutorial. I will be assuming that you have ESP-IDF tools installed and functioning on Eclipse, because there are many tutorials out there explaining installation steps. I will be assuming that you have ASP Homekit embedded to your ESP-IDF as well, because the installation steps are explained in details in Espressif website shared in the description section below, so there is no need for repetition. Now, let's begin with analyzing Homekit lightbulb example. Alright, so after importing lightbulb example from Homekit to Eclipse, let's start analyzing the provided code. In the main C file, let's go to the main function. Here we see that only one task is created, probably for initializing all the needed peripherals. In this function, of course, the task handler is passed. The name is stored in a macro. The required memory for the task handler, and the priority, of course. There's one thing to clarify here is that ESP32 works best with FreeRTOS, and the best way to do that is through tasks. And from this function, we see that there is no core specified to handle these tasks, and we know that ESP32 is a dual core processor, so it will be handled by CPU 0. I think we need some excitement here. Alright, so let's jump into the task handler and see what it does. Of course, first of all, we see that accessory and service pointers are initialized. Most probably these will be necessary for initializing the object that we are dealing with, which is lightbulb in this case. So after that, by the way, HAP stands for Homekit Accessory Protocol. I found that after some research. Okay, then we see that Homekit Accessory Protocol is getting initialized with Wi-Fi. As we can see, Homekit Accessory Protocol can be also initialized with Ethernet, since as we know ESP32 supports Ethernet. So if you don't have Wi-Fi network nearby, this doesn't prevent you from connecting Ethernet cable to your ESP32 and continuing with Homekit. Let's return to the main C file and speed up a little bit. Here in the HAP accessory configuration structure, the most important thing to notice is this accessory ID, where it is set to be lighting accessory, and by doing that ESP32 will appear as lightbulb in Homekit application. Let's see what other accessories are supported. As you can see, there is a bunch of accessories supported here, like lock, outlet, switch, thermostat, sensor, and more, which can be great for other projects, right? Even camera is supported. Awesome. Alright, let's return to HAP initialization process. Here we see that the HAP configuration structure is used to create the accessory, Then a dummy product data is added to the accessory. I believe that this is necessary for the hub protocol. Then we see that lightbulb service is created, and the initial state of the lightbulb is passed to this function. This means once ESP32 is connected to your Wi-Fi network, you will find your peripheral is turned on. This can be changed to false, so nothing will be turned on at the start. And after service creation, we see that the characteristics are added to the created service, and these characteristics are the name, brightness of the LED, hue of the LED, and this actually determines the color of the LED, saturation determines how intense the color is. And here actually, from the past parameters to these functions, we can get an idea of what types of value we are going to get when the user tries to change the color and the brightness of the LED through Homekit app on the iPhone. For example, here in brightness characteristic creation function, we see that the number 50 is passed, and I believe that this is the brightness percentage level that sets the LED once the ESP32 is powered up. And actually we saw that from the HomeKit app, right? Similarly, we see hard-coded values are used in the hue and saturation characteristic creation functions to set the LED color at the first start. Of course, these values can't be used directly to set the RGB LED PWM signals on time, so we need to use HSB, stands for hue, saturation, brightness, to RGB conversion algorithm, and we will talk about this in just a minute. Service characteristic add function returns 0 in success case, so all these functions are ORed together, and error check is done, and in case of any error, a message will be displayed in the serial terminal. Let's carry on. HubSet service write callback function is used to initialize the service interrupt subroutine where all the action happens. So for example, when the user tries to turn on or off the LED over the HomeKit app, this interrupt will take place, and all input data will be processed here. We will return to this function when completing Hub initialization process. Alright, so in Hub accessory add service, we add the service that we have created to the accessory that we initialized before. OTA update is also done here. OTA is a very wide topic. OTA stands for over the air, and it actually makes it possible to update the ESP32 firmware over any protocol that you may imagine. Bluetooth, Wi-Fi, even SPI, I2C. Slow, but yeah, it's possible. So let's leave this topic for the time being and make it for another tutorial to talk about, and let's carry on. So the accessory that we have initialized is added to the HomeKit accessory protocol database, so I expect that Wi-Fi will be initialized later on. Alright, in lightbulb init function, all 3 PWM channels are initialized. We will talk about PWM initialization process after finishing HomeKit accessory protocol initialization task, so we'll return to this after a bit. Alright, let's move on. In reset key init function, reset GPIO is passed, which is GPIO 0 in this case, and it is actually the boot button on ESP32 development board. Alright, so now let's see what this function does. So first of all, we see a handle pointer is initialized here. It's void type pointer, and to create the button object, IoT button create function is called. The first parameter to pass to this function is the GPIO number, which is 0. The second parameter that this function takes is the activation level of the GPIO, and here it's 0 of course because it's the boot button. When pressing on the boot button, logic 0 will be read at this pin, which is very standard. Parallel capacitor is used for switch to bounce, so there is no need to implement such an algorithm inside your code, and we will see this in just a minute. And I had actually explained in details the working principle of low pass filters, which can be used as a hardware solution for switch bounce problem. You can always go and see that video from the card shown above. Alright, let's get back and carry on with our code. IoT button add on release callback is used to initialize interrupt subroutine in order to reset network parameters. Once this interrupt is executed, The selected internet network at provisioning stage will be erased, and the ESP32 will not join that network automatically when reboot, and the preset network is executed inside the callback. As you may have noticed, there is no software debounce algorithm implemented before executing the preset network because of the used low-pass filter, which act as hardware debounce solution. The mentioned callback is executed when the boot button is held pressed for 3 seconds and no pointer is passed to the callback. IoT button add on press callback is also used to initialize factory reset interrupt subroutine, which is executed when the boot button is held pressed for 10 seconds. The difference between release callback and press callback initialization functions is that in release callback, after pressing on the boot button for 3 seconds or more, the moment the button is released, this callback will take place. On the other hand, in press callback, the interrupt takes place when the boot button is held pressed for 10 seconds or more. In factory reset, all network and pair information are erased after executing this interrupt. Now let's get back to Homekit lightbulb initialization task. This part of the code is production related stuff, so there's no need to comment. After that, we see the standard stuff that should be included in any Homekit project. Like here we see the MFI authentication is enabled, Wi-Fi is initialized, Homekit accessory protocol is started, Wi-Fi start, and at the end of the day, the whole task is deleted. This segment of the code is only executed in case of an error during the initialization process. We see that here in goto command, where both the hub accessory and the task we are running are deleted. And in order to have full control over red, green, and blue colors, we need to initialize 3 PWM channels, and this is done here. Just like in STM32, PWM channels run over hardware timers, and ESP32 has 4 64-bit generic timers to choose from. In this example, timer 0 is used in timer configuration. LEDC stands for LED control. And we see that high-speed mode is selected. High-speed mode features glitch-free automatic duty cycle change done in the hardware, so if you can just stay away from low-speed mode. 5 kHz and 13-bit resolution are selected for the timer configuration. I believe that this line does not exist in the original code. I had actually created a repository on GitHub regarding this project for any possible future modification, and I'll be sharing that with you in the description section below. On the other hand, in channel configuration settings, the important things to do are to select the channel number that will derive the PWM signal, and select the pin that will output the PWM signal. In my case here, I've chosen GPIO 33. You can choose any GPIO pin that you like. And of course, the timer number should be also selected. In this case, timer 0 should be selected because we had already configured timer 0 for the LED control. And we see that high-speed mode is selected. For this example, there is no PWM related interrupt, nor fading need. So we can disable this part. The duty cycle here is selected to be 100, but we had actually set the duty cycle to be 50% in home accessory protocol. So in our case, any value can be passed during the configuration. At the end, we see that channel 0 here is being configured. Then in order to configure the rest of the channels, we see that the channel number is changed with the pin used to output the PWM signal. Then it's configured. The same thing is done for channel 2. Having the needed PWM channels configured, now we need to process the data received over Homekit accessory protocol, and this happens inside the service callback that we had set before. Before diving into this callback and see what it does, we need to know the type of the data, which is hue, saturation, and brightness, received to this Homekit accessory protocol service. So to do that, let's have a look at HSB model. In some cases, this model is called HSV, which stands for hue, saturation, value. Value is used instead of brightness. Both of these names stand for the same thing. In order to understand what these parameters are, we need to study them individually. Let's start with the hue by looking at this model from the upside. So the hue here is the angle around the circle. so it can be any value between 0 and 359. In short, the hue determines what the color is. So for example, the hue value does not change along this line. In the HSB model, this circle is divided into 6 equal areas. And depending on the area where the hue value is located, the 8-bit red, green, and blue values are determined. Now to understand what saturation and brightness are, we need to take a vertical cross-section of the HSB model. By doing this, we are making the hue value constant at 180 degrees. And in this figure, the x-axis will represent the saturation, the y-axis on the other hand will represent the brightness. Notice how saturation and brightness values are expressed in percentage. 0% brightness will mean black and 0% saturation will mean white. Alright, let's return to our code and see how HSB to RGB conversion is done. In the lightbulb write service callback function, there are two important parameters to look at, and they are write data, which is a pointer that helps in obtaining important data related to the type of the callback, information related to hue, saturation, and brightness values, and whether the light bulb is on or off. And the other parameter is the count, which carries the number of the actions that need to be done in one callback at a time. So at the beginning of the callback, we see that an index and return variable are initialized with a characteristic pointer, and we see a loop is used to do every action at a time. As you may have noticed, inside the loop we see the reason behind the occurrence of the interrupt is checked, whether it's change in the state of the LED turned on or off, a change in the brightness of the LED, change of color, or it's a change in the intensity of the color of the LED. Alright, there are many if and else if statements are used inside the loop, so let's make this thing a little bit more readable. So as you can see, an action is taken depending on the reason behind the interrupt. Here we see that the status of the LED is updated, whether it's on or off. And depending on the past value, the LED will either be turned on with the brightness level or it will be turned off completely, and then all light bulb parameters are updated in this function. You will notice that this function is called at every characteristic event in order to update the PWM channel parameters with the new duty cycle values depending on the hue, saturation, and brightness values with respect to the 13-bit PWM signal resolution that we had set before. The HSB to RGB conversion magic occurs inside this function, which uses Anvy Smith algorithm. Personally, I didn't dive into the derivation of these equations, since it sounds like a long story. However, we can see here how the red, green, and blue colors values are set depending on the 6 regions that we had talked about before, which are determined by the hue angle. After that, the red, green, and blue values are scaled out depending on the duty cycle resolution that we had set before, which is 13-bit in our case. Note that this conversion operation occurs at every characteristic event, and we see that in light bulb set saturation, light bulb set hue, and light bulb set brightness event. This is of course done in order to make your peripheral, which is in our case LED, synchronized with the Homekit interface. Alright, these were the most important points related to Homekit accessory protocol. Now it's time to move to the practical part and see how this code will work out. Alright, so after all this work and this explanation, I suppose that compiling the code and uploading it will be a piece of cake for us, right? I cannot connect to my ESP32. Sorry for wasting your time, guys. See you next. Alright, that was a joke. So after uploading your code, we need to open the serial port that the ESP32 is connected to and restart it. So the ESP32 will print out two QR codes. One will be used for provisioning the network and the other one will be used in Homekit app in order to add your light bulb as an accessory. So to do provisioning, first of all, you need to turn on your Bluetooth on your iPhone and open ESP-BLE provisioning app. BLE stands for Bluetooth Low Energy. you can download this app from App Store. After selecting Provision Device option, your phone will start searching for the nearby BLE devices. And once a device is found, the camera will be opened to read the QR code. After establishing BLE connection, the app will search for the nearby Wi-Fi networks. The selected network, ESP32, will be connected to each time it's powered up. Make sure that your iPhone and the ESP32 both connected to the same network, so it's possible for the connection to be established in Homekit app. Okay, now we are done with the provisioning. Let's open Homekit app and add our light bulb so we can start playing with it. To be able to add an accessory, we need to read the related QR code. And once the device is identified, the room of the device is selected. This feature is used in order to group your HomeKit accessories depending on their rooms. Selecting the name of the device is quite important if you are going to use the voice assistant Siri. By using the name that you give to your device, it's possible to control it using voice commands. And here is an example. Hey Siri, turn on RGB LED.
Okay.
Hey Siri, change RGB LED color.
What color did you want for your light?
Red.
Okay, red it is.
Hey Siri, turn off RGB LED.
Okay.
And here is an example of how to interface your smart light bulb using HomeKit app. Okay, so after watching this tutorial, I suppose that you guys are able to build anything related to HomeKit, starting from smart light bulb to building your remote rocket launcher. This brings me to the end of this video. If you have learned something new, please like, share, subscribe, and tell your friends about useful electronics. Thank you for watching, and bye bye.